Major support has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Panama Buena Vista Union School District, and the Kern High School District. With additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Today we're at Bakersfield Plastics, joined today by Bill Lever. Bill, thanks so much for having us today.
Thanks, Devin. Very nice to have you here.
Wonderful facility. Tell us a little bit about the shop.
We do a number of things in plastics, and of course, showing all the students, it's important to measure things because that's how you know you're right or not, and your customer is going to be happy. We do things like carpentry in plastic, so we could have used plywood, but we use clear plastic instead to make all kinds of things like retail displays or guards at the cafeteria for food. We do those kind of things.
Plastic's a pretty versatile material, and our viewers are somewhat familiar with it, but they may not exactly know where it comes from or the process of creating and working with plastic. So explain that process a little bit.
Sure. Plastics have been kind of an accident. About 100 years ago, people experimenting in laboratories found weird things in test tubes, and they found that they would work better sometimes than wood, better sometimes than metal, than natural fibers and ceramics. And so many things are made of plastic because it's easy to form and it's very easy to make repetitive things, lots of them, very cheaply. So plastics are a good material to work with for lots of mass production things.
And if you're going to create products through mass production, you're going to make a lot of something and they all have to be very similar, then there needs to be a lot of precision, and the tools that you utilize have to make sure that some of the parts you make have a sense of uniformity, that they're all the same. And
Sure.
So there's a lot of tools here that enable that.
Sure, if things are going to fit, they've got to be very precise. And think about nuts and bolts. Nuts and bolts, before the American Civil War, there was no uniform standard for them. Now we have a uniform way of doing it. It's very precise, and you can test whether these will work anywhere in the world. So when you buy 1/4 inch 20 nuts or bolts, you know what you're getting.
Now that's very important when you do have special projects come in. And I understand that there's a project that's come in that we'll be kind of walking through as far as concept to product today.
Yeah, Devin. Mike brought by a project. It looks something like this. It's got some squares made out of plastic, and I think you trace lines inside of them. Some of them have 2 lines in them going one way. Some of them have 2 lines going the other way. There's several of these things, and we'll show you how we're going to make them.
So we start off with a sketch, right? A concept with some measurements built in as far as ultimately what we'd like these to be. And so where do we go from here?
We go and we measure them, and we draw them on a 3D computer. So we'll make a 3D drawing on a computer, and that will then be used to go to a machine that'll cut them.
How long of a process does this generally take?
It depends how complicated it is, and depends how precise something needs to be. These are not really all that precise, so we don't have to go to 10,000ths of an inch, but we'll be able to measure them, draw them, make a cutting file as to how it'll be cut. And it's interesting, this same file could be used on a laser cutter, it could be used on a mill, it could be used on a 3D printer even. So the same concept of drawing works backwards and forwards with different types of processes, so it's worth learning.
It's tremendous, Bill. So when we come back, we're going to head into the computer lab and we're going to take a look at how this is processed digitally to go from a file to the real thing. Back here at Bakersfield Plastics, joined again by Bill Lever. Bill, we're moving along in the project phases. Tell us a little bit about where we are right now.
We're in our computer lab, and Jake is going to show us how we use the computer to design things. He's got the drawings from the project that Mike brought by, and he's going to measure them up, and he's going to make a 3D drawing that'll be useful in a lot of different ways if we want to cut it on a mill, which we will do, or if we wanted to laser cut it, or if we wanted to 3D print it. We could do all of those things with the drawings here.
That sounds great. Well, Jake, walk us through a little bit of this process, how you kind of get things started and what we're working off of here.
Okay, so we're using a software called Fusion 360. It's just a 3D modeling program, and it has all kinds of great tools. So first thing you do, this is our project. This is a regular piece of paper. So I know that that's 8.5 by 11 inches. So I would just draw these tools. I choose which plane I want to choose. So I'm going to look down on it from the top.
Very similar to a coordinate plane that students might explore in class, X and Y axis.
And I'm going to use this rectangle tool to just draw it, and it lets me put in the measurements here. 11 on the X axis and 8.5 on the Y axis. So then I'm going to measure these little things I got to put in here.
Now tell us a little bit about the tool that you have here. It looks a little different than some rulers that some of our viewers might be familiar with.
Yeah, it's called caliper, and it has a digital reading, so you stretch it to how far you need, and it gives you a pretty accurate measurement, but not as accurate as the micrometer that Bill might have shown you. So this is about 6 1/8 of an inch or so. And so I'll just draw more rectangles to get what I want. So I'll just draw 3 in general, and then I'll measure them after the fact. Let's see, and measure the width is about 1/4 inch there. So I'm going to just define them. So make these 0.25. That's right. I also like to put like a middle line on this rectangle just to make sure I get them oriented right. This is just called like a construction line. So this doesn't really affect your drawing, it's just there to kind of help you visualize what you're doing. And we have all these other great tools here called constraints, which that helps you kind of put them where you want them to put them. So I'm going to use this one called symmetry. It lets me center them around this center line here.
So our viewers might reflect on the concept of symmetry as if you were to fold a line right through the middle of it, the shape would be identical on both sides of that line. And so this is a great application of that skill and that definition.
The last thing I would do is measure these outside edges to the edge of the paper, which looks like it's about 3 1/4. That's what we'll do there. So I'm going to define that here. All right, and then your drawing's pretty much complete. And to make it into a 3D shape, then we use this extrude tool, which lets you take your drawing and pull it into a 3-dimensional shape. Now I'm going to choose 1/8 of an inch. So you look at it from the side, you can see it's 1/8 of an inch thick, and it's got your holes through it.
So we think about the concept of length and width when we had that flat surface. Now we're talking about height as kind of, if we think about volume, as the thickness of this, what will ultimately be our final product.
Yeah, you see now it has a Z-axis instead of just an X and Y axis.
Now that's interesting because a lot of our viewers may only be familiar with X and Y. Now all of a sudden we have this third dimension of height or depth, or thickness in this case, and that's referred to with another letter, the Z-axis. So that's a whole other coordinate to start to consider as we come off of just a flat plane now onto a 3-dimensional space to work through. That's tremendous. So now we have this file is complete. Where does it go from here?
Well, we have to actually get it ready to go on the mill, so we use this CAD program here. And this is how this computer communicates with the other computer. So you make a new setup, and you'll tell it the dimensions of your stock. And this has a little offset that I don't want to use there. You see you have our coordinates right here?
Right there. That's the origin.
That's right.
Yeah.
But we usually like our origin at the top left, because that's where it's at on the mill.
Excellent.
So we're going to make it the same right here. So now it's on the top left, and it matches up with out there, and then you just choose a way to cut it. And I'm going to use this cutting called a 2D contour. So essentially just traces around an edge and does it at whatever depth or multiple depths that you want to cut at.
So before this even goes to the mill, there's even a way for you to get a sense and see exactly how this is going to cut before we go out there.
Yeah, that's right. This is called the simulation feature. Essentially, it has like a representation of your end mill here and your material, and I'll press the play button here, you see what it does.
So it's going to start with this center slat here, then cut around the outside before it gets to these other two. And so we'll know that before we even take it out to the machine.
That's right. And so now you'll see it's going to cut exactly what you want before you get out there and waste your material.
Jake, this is tremendous. Thank you so much for walking us through this process.
Oh, you're welcome.
So when we come back, we'll go ahead and put this into the physical world and make it come to life. We're back here at Bakersfield Plastics, joined by Bill Lever. Now, we're ready to go ahead and put everything into practice and get our project made. There are some conversions that you want to have memorized, but a lot of times what you work with is easier to reference than to calculate. So tell us a little bit about that process.
You're right, Devin. You want to know how to do stuff, not remember it all. And so what we're talking about here is fractions and decimals of an inch. And they're both very useful. Some ways you're less likely to make a mistake maybe in decimals. And so converting one back and forth is something you want to be able to do, but you don't need to be able to remember this whole chart. But ones that are really important to remember are like half an inch would be 0.5000. And everybody has it easy. They know that half a dollar is 50 cents. They know that a quarter of a dollar is 25 cents. Everybody already knows this, but when it comes to math, some people, they think it's too complicated, but it's not. So a half of a quarter of an inch is an eighth of an inch, and the decimal there is 0.125. And if you add 0.125 and 0.125 again, you get 250.
Now we're ready to put it, and we're back here with Jake. So tell us a little bit about where we're at right now with the file that we just created.
Okay, well, we have the file loaded in the computer, but we just have to have the machine set to make sure it knows the Z location. So what we're measuring is from the end of this tool, like this is the Z finder here. It's 2 inches tall, and we're going to tell it, the computer, that we want to find to the measure the top of the material. So we'll set this right to 2 inches, and you can see the dial go there. It's going to move towards the 0. And like Bill was just showing on the chart, we have to measure to the top of the material, which we know is about an eighth of an inch thick. So we're going to take what we do know. We know that this is 2 inches high, and we're going to tell the computer that it'd be an eighth inch off the plate. So we're going to type in 2 minus 1/8 of an inch, or 0.125 is going to be 1.875. And so now the computer knows that. So it's not going to go too far down. It'll just go right to the bottom of this material, right above the plate.
The way we had it set up on the computer is that this is the origin right there. X, Y, and Z goes down into it. So you're setting up what's going to be the point right here. You have a little extra material here on the outside, don't you?
Yes,
so
that's
we're
right.
going to cut, we're going to start cutting in the center like we saw. Then it's going to go around the outside and take just a little bit, and then it'll come back and do the insides. But he's trying to establish where he is right here, and nobody's perfect. You can see we've cut this aluminum plate a few times, so we don't want to do that today, but it's not a disaster if we do.
Okay, so just have to get this on here. We stick it on with this double-sided tape here. Excuse me. And let's put your origin right up here.
The aluminum plate's the exact, and you just get it over the edge a little bit. Is that right?
Yeah, that's right. I make this piece just a little bit larger than the piece. It's a 1/4 inch larger both directions. So that way I have a little room for error, or my error. All right, that's set up, and we just press this green button here to start the whole thing.
It's now cut 120 thousandths deep.
Now what's interesting too, at every step of the way, as the surface moves, you can see the location of the mill along X, Y, and Z coordinates.
The trick is that the tip of the tool has an X and a Y and a Z location at all times. So that's exactly where the tip of the tool is right now, 5 inches and just a little over an inch.
So that whole process took about 2 minutes and 45 seconds. Whereas doing that by hand may presumably take a little bit longer if you really have that mind for precision.
And wouldn't have been as accurate.
That's right.
So you'll see this in another episode. And this is paper that protects it. We just peel the paper off, and there's the part that you saw being drawn just a few minutes ago. And now it's a real deal.
From vision to finished project. That's tremendous. That's great. Well, Bill, thank you so much for allowing us
Devin,
into
thank
the
you
shop
very
here.
much. We
And of course,
appreciate your coming by.
as customary, whenever we stop by, we want to make sure that we award you with an honorary Do the Math tile.
This is quite an honor. Thank you very much. Unexpected.